Hello everyone, my name is Fazeel Ahmed and let's continue with our course of Continuum Mechanics. I am following Continuum Mechanics for Engineers by May's third edition. Today we are going to be discussing topic 3.11, the octahedral state of stress. So first, what is the octahedral plane? Let's move to this wonderful tool called geogebra.org. Here, I have plotted a vector. You can see how it has equal angles with all the three axes. So this is the main foundation. Such a vector which stands in the middle of an octant of the 3D space, sharing equal angle with the three coordinate axes. Since there are 8 octants of the 3D space, hence we have 8 of these vectors, and the top 4 vectors are shown here. The 4 bottom vectors will be similar. The plane perpendicular to one of these vectors will be called the octahedral plane. Just like there are 8 vectors, there will be 8 octahedral planes. So, why do we call them octahedral planes? Well, let's look at all these octahedral planes that are possible. These slanted faces make a shape around the center of the body, around the center of the axis. And looking at the top projection of those faces, we see this. This 3D shape that will be formed by these planes is called an octahedron. Hence the name octahedral plane. A regular octahedron is shown here. So you can see how we have gotten the name. Having a visual idea of what it is, let's get to the math. We represent the 8 normal vectors as such. All the components have equal magnitude, but they may have different directions, hence the plus minus signs. And the square root being divided is just to make it into a unit vector. So let's find the stress tensor on this new configuration. We do have a prior condition. The original configuration or the original coordinate axis should be aligned with the principal stresses. So the stress tensor prior to the transformation is this. Now we have to find the traction vector on one of those octahedral planes. We know the traction vector is the dot product of the stress tensor and the unit normal vector to the plane. So we decide to take the unit normal vector in the first octant where all the 3 components are positive, and here is the traction vector. Simple and easy. Now we get to what would be the normal stress acting on that slanted face. Well, for all, but for that, for that, all we have to do is to take the product of this traction vector with the unit normal vector, and that is easy as well. We get something interesting. The octahedral normal stress is equal to the magnitude of the spherical state of stress, and it is an invariant of the tensor, so it will be equal in all the 8 octants, regardless of what unit vector we had decided to start with. Similarly, let's see if the shear stress gives us something interesting. The shear stress will be the difference of the magnitude of the traction vector with the magnitude of the octahedral normal stress. That is written as this equation, which simplifies into the following relation, which can be further reduced to this relation. Here is the derivation for these relations if you so fancy. Now, what does this last relation signify? Signify? It says that the octahedral shear stress is a function of the second deviatoric stress invariant. One of the uses of this octahedral shear stress is that this shear stress and the deviatoric stress tensor tie up together in something called the von Mises failure criteria, which of course deserves a separate video of its own, and it will be discussed later on. For now, just the definition and the introduction of the uh, topic is sufficient. When I have made that video, I will put its link under the description. That's all for today. I hope that this video was helpful to you. If you liked it, please give it a rating. I'm just starting out, so any support you can give me will be massive. If you have any questions, just ask below and subscribe to show your love. Remember to smile, remember to drink plenty of water, stay safe, and I will see you in the next video. Bye.